All right, so looking at this Jupyter home here, you see that I have this Lecture 8 notebook. This is an IPython notebook, and we can simply click on it. So you see I'm recording this in a virtual machine, but I'm piping it through the local network. I have a Jupyter server running on my laptop, so we can just open this. It's beautiful. Right, and we have to select the special. So I'm using a virtual environment here um, that I made specifically for this course. So I have to just set this one, set the kernel. Kernel means this is the process, if you will, in the Jupyter notebook that works for me. So we're looking at this. It's a data set that has been published by the UCI, the University of California. And this is a data set that looks at single household power consumption. We're looking at this data set in a way, first of all, I mean, this is the structure of the data set. It has these, it has some parts of a date, it has a time. You get the global active power for every household, typically in this case in kilowatts, and also you get the minute averaged power that is reactive. So this is, it could be kilowatts, but it could also be kilovolt amperes reactive in that case. We get the minute averaged voltage. We also get the current intensity and so on and so forth. So it's a lot of data, but let's just look at it. So we know that libraries exist, and so we should use them somehow. I put up a little bit of text between the cells. So these are all Jupyter cells, right? This is just a markdown cell, but here we have code, actual code. Let me just, maybe I can put the thing in full screen. Nice. So this is a cell with code inside, and here it's basically loading the libraries. So it can execute that cell, pushing Shift Enter, and it works. Isn't that beautiful? So what I'm trying first is just navigating to the right folder, and then we load the data set itself. As you see, I've written a small function. That function actually does something very interesting. So this is the part where it's just reading the file, fair enough. But the pandas is a de facto standard way of handling data frames. And pandas data frames, they have some functionality that is really useful. So in the data set, there are some numbers that are not available. So not a number. And these destroy our typical vanilla calculations. So if you wanted to calculate the mean, for example, and you run across something that's not a number, then you need to adapt your program to deal with it. So it's kind of cumbersome. Instead, we clean it right at the import, and this fill_na function is just doing that. So now let's go ahead and execute this, and then have a look at what the columns are. So for example here, I mean, we've seen this in the front, right? And in the first cell, there was already that we had a date and we have a time, we have a blah, 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 blah. So all these elements are part of the data set. We can just plot it to get a visual feeling of it, but this can sometimes be distracting too. But in this case, it works quite nicely. So we see that the power here that is being drawn over the sample indices. Sample indices, as you see here, they reach 2 million. So it's I mean, more than that even, right? So it's a rather big data set. I mean, it's not a big data set, but it has some samples that you don't want to do this yourself. Okay, we have plus we have some more elements. For example, here we see the varying of the voltage. Again, just visually, I'm not talking about variance here or anything, it's just visuals. Also well, here we have submeterings, we have another submeter, and so on and so forth. We see that they have some similarities, right? So they have these gaps here, these big gaps that looks about the same time. We will maybe have a look at that later, what that means, or if they do vary with one another. It would be an excellent use case for the correlation, of course. And we also get the third meter. This is, I forgot what it was, but it says so in the market, submetering 3, that was, electric, water, and air conditioner. Okay, so you get some interpretability of the data set. Now, the cool thing about pandas and the data frames that we can use in there is that we can get a summary of a data set very quickly, right? So we see that we have just over 2 million data sets, the data samples in the data set. And we see that they are pretty much the same. So we get more or less the same value here. So we probably have very evenly distributed Northern numbers inside. The mean, however, is varying quite widely. So we have something like 10 to the minus 1 here. We have 10 to the 0 here. So the global active power and the global reactive power, they're quite different, for example. We see the standard deviation, we see the minimum, and these are the percentiles that we talked about. So this would be Q1, this would be Q2, and this would be Q3. And we also get the maximum. These are just this all comes out of this describe function. So this describe function does not give me some higher order moments, but it gives me the most important, the two considered most important, the mean and the standard deviation, which are 2 moments, right? But so this goes a long way of understanding somehow what this is. So the actual computation of the means, we can do this ourselves, right? We can look at how means are calculated. So we go for a column, and we're selecting first for, we don't want these NAs, because why would we? So we're first querying the data set, or the column. We're querying the pandas library to filter our column for not numbers. And then we just do the sum over that previously filtered element, after which we divide, so that is exactly the mean. And nice. So we can get some additional elements. I mean, this is exactly what we're seeing up here. So the mean is 1.091. This is exactly the same as here, right? Perfect. And so on and so forth, huh? Nice. So here we see that 240, for example. It's just here, I mean, we have 240 because here's the 10 to the 2 at the end, right? So this is exactly the same. Cool. So the standard deviation, we can also look at is how does it work? Again, we filter again. So this is the first part. We filter, same as before. Now we calculate the mean. This time we just we take care. I mean, we're doing this this operation here where we let NumPy do this for us, because NumPy is powerful and fantastic. And then we're calculating the standard deviation ourselves, right? So this was, you remember this from the slides, this is a central moment. Therefore, we subtract the mean from every sample. And then I mean, it's a second central moment, so we have to square the whole thing afterwards. And we divide by the number, because this is what we do in statistics typically. And we can also look at this. And without too much scrolling, I promise you that it will be the same as the number up top. You can check for yourself, though. Just go check for yourself. So we do the same thing for the median. This is exactly the second quartile, as I told you before. All right, it splits the data in 2 parts. We're looking at, okay, so we basically want the middle value. So we sort it first. So this is a beautiful function of NumPy again. We sort it after filtering, of course, because we don't want nans in there. They don't make sense. We find the length of this, and then we figure out, okay, what should we do? Because if you remember, the median was this. It depends on if our data set, if our vector is even or odd in terms of length, and we can do this exactly in here. So here is a check: is our length, is it even or is it odd? So if we divide by 2, or this modulo here, this is L modulo 2, so this checks for the remainder, we divide L by 2 and we check for the remainder. So for example, if you have 3, 3 divided by 2 is 1, remainder 1. So the remainder of this, if it's 1, then it was an uneven number, an odd number. And if it's odd, then we just take the middle. I mean the middle value, which is just the index plus 1, because Python is a zero indexed bitch. Okay, otherwise we have we need to take the if we have an even number of elements in our vector, we just have to take the two middle ones and average them. This is exactly what's happening here. Cool. Oh, I need to execute this. And again, we get the same numbers as above, I think. Good. The quantiles pretty much work the same way. We just sort, we figure out where to cut it. This goes exactly according to the slides. So we're looking at the length, we're looking at the sorting, and we stop at some point. So this is the first quartile, and the third quartile you can do on your own if you wish so. I encourage you to do this because it's a handy thing to understand. But again, this was just single values, single values describing features. Now let's look at what is actually the experimental distribution of the data. So the next step is quite huge computationally, because, or at least can be. So if we look at these histograms, the histogram is just, again, right, we sample a random variable that we don't know. In this case, we have this already done for us in terms of the dataset. The dataset is the realization of a random variable that we don't know. And now we can just put this into bins. So there would be a bin from 0 to 1 here, and this bin is quite full. And there's another bin from 1 to 2 or something like this. Here, this is also quite full. And then there's more bins that tend to be gradually less filled. So what this does is it sorts our data and then assigns it to bins. And these bins are, well, in this case, we have 10 bins, and they are evenly spaced. So this is a lin space. This means it's evenly spaced. And then we just walk over every element in that sorted part and just compare with all the bins boundaries and sort it into the according bin. All right. Yeah, this is already executed, so let's go for let's go for it. Cool. So you see, I'm doing it 3 times now. So I actually could have separated this into 3 function calls just to understand a little bit better how computationally intense it is. But we're seeing that we have just about 2 million, just above 2 million data samples per feature that we're looking at, because we're looking at 3 features here, and it worked quite quickly. So this is a very slow machine. I mean, now that it's virtualized. And well, we can also look at the plots now. So this is pretty much the same as at the top here, which is expected. And then we can look at all the rest. I'm just going through this, and you can spend a lot of time. You had already more of a background in terms of energy, so you can have a look at what these are. But these are just counts. This is just counting, and we don't have any PMF here. We don't get any probability mass function. This works pretty much. We're getting there. Huh? So, for example, these here we can actually see we can actually see that this one is this looks nearly normal. This looks like a normal distribution, whereas these two are just, I mean, they are either truncated or very much shifted. Yeah, exactly. So is it really a probability mass function, and is it close? So how close is it to the density function? Okay. So why can I not? Oh, okay, it's executing. So Yeah, in fact, they all sum to 1. They all do to 1.0, right? So this is quite close. However, we already have more than 2 million data points for every feature. So um, this is not terribly surprising because, of course, there's also internal rounding and yeah, so, but still, it's interesting to see. So this third one I just told you, right? The third one looks like a normal distribution. I didn't even read it. Right, so if we wanted to build this probability mass function, this approaches this. So we're doing this as exactly as in the slides, and also here we can just look at this. It turns out this is exactly what we expected, right? So the single pieces here, the single peaks, Dirac-like peaks, they just represent the probability of being exactly in that point. Okay, so this describe function is really powerful. So we can do this for simple single features as well. So it's not just for we don't have to do it for the whole data set. We can also do it for a single feature. Um, let's see the global active power. It looks like this, right? So, but with 2 million data points and the certain mean, and we have a standard deviation. Should this be normal? Or does it sound to you like a normal distribution? We can have a look, of course, how this looks like. It takes a minute. I mean, not a minute, but it takes a while to get this. But looking at the data itself, you can already see that the minimum is small and the maximum is comparably large. Excuse me for that. That was not wanted. Okay, looking at the density now, we see something interesting. So we see a two-peak thing. This is this explains, of course, why it's behaving like that. It's not exactly normal, but there is a second peak here that is really screwing things up. So it's definitely not a normal distribution. Here it seems that it's the same thing again. Yeah, these are exactly the same. Okay, so we can also look at the reactive power and check how far they are apart. And because so typically active power and reactive power, they should be close because we have this issue of transport, right? So the typical parts in power engineering are always trying to keep the two in balance. This is one of the big motivation for smart grids. But we see that there are a certain difference between them. So if there's any sort of difference, that this is always an indication for a mismatch, and mismatches are bad because that way you require more current from more power, and you require more current instead of requiring more voltage because the voltage is very rigid. It cannot can't really jump a lot. And luckily enough, it is rather stable. So this is a beautiful normal distribution. This is really nice. So looking at the final piece is the correlation or covariance of features. And here we're looking at, I encourage you to look at this specific line very closely. It's a scatter plot of active powers greater than 0 versus, so to speak, versus the voltage for the given part of active power greater than 0. And here we can see how they vary with one another. This is interesting for all kinds of applications, and we can do the same for reactive power and the voltage, or the active power versus reactive power. And so a perfect correlation would be very surprising, to be honest. But we see that there are some elements that are um, definitely. So this is non-normalized, by the way. This is just the scatter plot, right? And if we look at the correlation itself, in fact, then we see that there's actually not, I mean, not a huge correlation between reactive power and active power. So the correlation is unfortunately not very strong. But the thing is, the voltage correlates negatively. So this again, it's linear correlation. So this is specific. But if we remember back from what I considered, I said, look at submetering 1 and submetering 2. They have somehow the same gaps. Let me scroll up again. So in the plots here, where's the second submeter? Episodes of 1 and 2, they have kind of the same gaps here, but it turns out that their correlation is just negligible. And the reason for this, I mean, even though it looks a little bit interesting, but if you look at the correlation between the two, so submetering 2 and submetering 1, the correlation is just 5% or 0.05, which is, I mean, it's very low. And funnily enough, the submetering 1 and submetering 3, they have a higher correlation. The thing is just, if a couple of dozen values are exactly the same, in the scope of several million, this is just not a very powerful impact. So these statistical values here, they help you draw conclusions, even if the visual inspection doesn't really gives you another idea. So you can actually fact check your intuition with this. This is basically why it's so useful. Okay, I hope you learned something today and you enjoyed a little bit of the hands-on. Again, please feel free, and I encourage you to play with a Jupyter notebook. It's a beautiful tool. You can also don't forget to do the correlation stuff if you haven't done it already with the expectation. This is just a nice handy exercise for you. I strongly encourage you to do this, and I wish you a pleasant Pentecost week, and I'll see you again in 2 weeks.